All right, so we're going to do 9.3 today. We're going to do testing about the population mean. Okay, so we've already done our confidence intervals on the proportion and the mean, and then we talked about doing a significance testing about the proportion. That was in a 9.2. So in 9.3, we're going to talk about the significance testing about a population mean. Okay, so it's very similar to our confidence interval. We're going to have the same three conditions that need to be met. Okay, so the conditions that need to be met are, number one, it has to be a random sample. Number two, you cannot oversample. Okay, you can only sample up to 10% of the entire population. And three, we're going to have the large counts. Now remember, in the large counts for the proportion was that this was greater than 10 and this was greater than 10. Okay, so that was for the proportion. Obviously we do not have a proportion, we don't have a p here, right? So for the large counts in our mean is just the same as when we did the confidence interval. We said that n has to be greater than 30. You have to have more than 30 samples, okay? Now, what did we do if we did not have 30 samples? We did the same, what we did in confidence interval was what? If n was less than 30, then we had to do a dot plot, right? We have to do the dot plot to see, make sure there is no skewedness. So make sure it's not skewed or no outliers, right? These are two things that we had to check, okay? So in other words, let's review. The three conditions for a significance testing about the mean is that it has to be a random sample. You cannot oversample, it has to be less than 10%. Large counts, n has to be greater than 30, okay? If n is for some reason less than 30, then you have to do a dot plot to make sure that there's no skewedness or no outliers, okay? So these are the conditions that have to be met, right? And those are in a green box on page 585. You can go ahead and look at those. So let's do the example. In the example we have, here are the lifetimes in hours of 15 deluxe AAA batteries from the company's simple random sample. Okay, so check to see if the conditions for the performance significance tests are met. Okay, it's a random sample. Does it say it was a random sample? Yes, it says it was a simple random sample, so we were good with that. And we definitely are producing more than 150 AAA batteries, right? So it's going to be less, 15 is less than 10% of the entire population. We're good with that. Large counts, okay, we are less, n is 15 here, so we are not greater than 30, so we cannot immediately say we're good to go. We are less than 30, so we have to do a dot plot to make sure there is no skewedness or any outliers. So if you look at the solution, it gives you the dot plot, and it looks as though there is no skewedness or outliers. Okay, so that we can say now that they check all the three conditions. All right. So how do you actually calculate? How do you do? Again, we're going to have to calculate the p-value, right? We have to calculate the p-value. So in order to calculate the p-value, when we did our confidence intervals for the mean, we had the problem where we did not know if this was the population, and we took a sample here, okay? Our problem was what? This is what we're trying to find, right? And we're going to get one of these, okay, from in our sample population, in our sample, right? In our sample, we're going to get this, and it's going to have one of these, and we're going to get one of these from our sample, okay? The problem is that we have no idea what this is. Normally, this would be what? This would be this guy over here, but we don't know. We do not know this, and we had the same problem when we were doing the confidence interval. So we decided we said that we're going to use what is called the t-distribution. Correct? We're going to have to do the t-distribution. So we're going to do the same thing for our significance testing. We're going to do a t-distribution. Okay, and just like we did in the proportions, we're going to have to find the p-value. To find the p-value, we need to find the test statistic, right? We're going to find the we're going to find the standardized test statistic. Okay, so the standardized test statistic for here is going to be obviously within a t-distribution, right? And it's going to be what? It's going to be what we got in the sample, and we're going to subtract that from what the host says, all right? And we're going to go like this, and we're going to use the standard distribution that we found from the sample. We're going to use the sample mean, and this was the HO that we're trying to do the significance testing on the mean of the population, and this is nothing more than the sample size. Okay, so this is how we're going to do this. Right? So if you go to page, where are we at? So let's go ahead and see if we can do this. So let's go and do the, we're going to set up a significance testing for the batteries that we just did, and we're going to say that the HO is that this is equal to 30. Okay, this is equal to 30, and then we're going to go ahead and see, let's see, the HA would be, we want it to be greater than 30, right? So this is what we're trying to prove. We want it to be greater than 30, right? Okay. So first of all, we're going to have to find the mean or the X bar. We're going to have to find this and this, right? How are we going to find that? Well, we have the 15 things, right? We have the 15 data points, and we're just going to populate the L1, and we're going to do a 1var stat, right? If we do the populate the L1 in your calculator, stat, edit, and do L1, and then do the stat calc, and do the 1var stats, you will find what? You will find that the X bar is going to be what? The X bar comes out to be 33.93, and the standard deviation here is going to come out to 9.82. 9.82. Okay? So this is all we're going to get from 1var stats, right? So let's go ahead and calculate the actual test statistics here, right? The standardized test statistics. So we're going to get this guy, 33.93. We're going to subtract it from what the host says right here, right? 30. And then we're going to have this guy, which is 9.82. And we had a sample size of 15. Okay? So if we do that, we're going to get, what? If we do that, what do we get? We get 1.55. We're going to get 1.55. Okay, so our test statistic is going to be 1.55. Okay, what's our degree of freedom here? Our degree of freedom was always n minus 1. So 15 samples minus 1 is 14. So our degree of freedom is 14. So if you go to your table, I think it was table B in the back of your book. If you look up the degree of freedom on top of page 589, you can see that there is not an exact number for 1.55, okay? If you look at it, there's 1.35 and 1.761. So you know that's going to be in between that somewhere, right? So in other words, the p-value is going to be what? The p-value is going to be between 0.10 and 0.05. In other words, it's going to be between 5 and 10%, okay? Between 5 and 10%. Okay? So if we use an alpha value of 0.5 here, what do we get? If the alpha was 5%, what can I say? I can say that the p-value is going to be greater. I don't know what it is, but it's between 5 and 10%. So I know that the p-value is greater than the alpha, which means what? We failed to reject the HO. We do not have convincing evidence for this. Okay? All right, so that's that. Now let's see if we can do the two-sided tests. So on a two-sided test, what do we have? Suppose, let's go to page 589, and we're going to do the example on that one there. All right. Okay, so what do I have? I have, suppose you want to perform a test of the hoe is mu is equal to 5 versus the high where mu is not equal to 5. Okay, so we should have alarm bells going off here, right? What is this? This is a two-sided thing, remember? When it was not equal to, we had two-sided, right? Okay, so this should be a two-sided test. Okay, and we're going to do an alpha of 1%. Alpha of 1%. Okay, so, and we do a random sample size of 37 from the population, and we get x bar is 4.81, s of x is 0.365, 4.81. So I get 4.81 for x bar, and I get for this, I'm going to get 0.365. A, explain why the sampler result gives us some evidence for the alternate hypothesis. The alternate hypothesis is this, which is what we would like to prove, right? Well, mu naught is not equal to 5. Well, we got x bar was 4.81. So it's not equal to 5. So we have some sort of evidence, correct? B, calculate the standardized test statistics and the p-value. So the standardized test statistics is right here. X bar was 4.81 minus the mu naught, which was 5 here. S of x was 0.0365. Square root of how many samples? Well, I think it was 36, right? N was, 37, I'm sorry, 37, 37. Right? If I do that, what do I get? Looks like I'm going to get 3.17. I'm going to get 3.17. Actually, it's negative 3.17, right? Because it's a negative value here, okay? Because this top is going to be negative, right? But actually, it's the same thing, because whether it's positive or negative, because the t-distribution, right, and a standardized, whether it's over here on that side, it's the same thing, right, because it's symmetric across the mean here, right? So 3.17, if I look at 3.17 at a degree of freedom is what? What's my degree of freedom here is, n was 37, so degree of freedom is 36. If I go to table B, unfortunately, I do not have a degree of freedom of 36. Okay, and when just as though we did when we did this for the confidence intervals, if you have a degree of freedom of 36, you're going to go to the next closest lower degree of freedom, right? So the next closest one that's lower than 36 is 30. So you're going to use a degree of freedom of 30 line there, okay? If you look at that between 0.303 and 0.3385, because that's where 3.17 falls, right? 3.17 falls there. It's between 0.1% and 0.25%. So you're going to have between 0.1% and 0.25%. However, since it's a two-sided, you have to multiply it by 2. So the p-value is going to be between 0.2, and multiplying this by 2, and multiply this by 2, I get 0.2 or 0.5. So my p-value is somewhere between 0.2 and 0.5%. Either way, it is smaller than alpha. So the p-value that I calculated is smaller than alpha, which means that I get to reject the hoe. And I have convincing evidence that, yes, indeed, the average, the population mean, is not equal to 5. Okay? Obviously, you can do the same thing. You can do this in your calculator, right? If you use your calculator, okay, And that's on Technology Corner on page 590. All right, and that gives you the how to do that. You would use the TCDF function. You'd use a TCDF function to find the actual. You can use the TCDF. Okay, in other words, once you find, say, let's go. So it's using the battery. It's using the battery one there. So we had 1.55. Remember, we were going from 1.55. We're going from 1.55 up here, right? So this is because this is what we're trying to find, right? So that would be what? So TCDF 1.55 to 100. A degree of freedom of, what was it, 14, I guess? It was 14, right? 14, yeah. So you can go ahead and put that in and find the p-value that way. Okay? All right. Well, we're going to stop right here today.